By the end of this video, you will be able to relate how the M&M model is analogous to radioactive decay. You will be able to describe how the relative proportions of the parent and daughter isotopes can determine the number of half-lives that have occurred, and you will be able to interpret the half-life graph and use it to determine the ages of rocks. All right, so hello there. So today we are going to continue to talk about geologic time and the absolute age. How do we figure out the actual absolute age of a rock by simulating radioactive decay? And we seem to have more food here again. Always a good thing, except this time instead of popcorn kernels and popcorn, we're using plain M&Ms. The M&Ms are good analogs for parent and daughter isotopes because these M&Ms, what do you notice is written on some of the M&Ms?
An M?
An M, the letter M, yeah. So the letter M, we can make sure that we have, I think we opened up 2 bags each, and there should be 28 M&Ms in the 2 bags. So if we can make sure that all 28 are M side up, because that's going to be our unstable parent isotope, the one that is going to decay. These are the unstable parent isotopes, and we're going to call that, for the M, M&M, right? How about that? We're going to close this and shake it, and after that shake, we're going to open it up, and we're going to remove the ones that are changed, that have decayed into the blank side up. In other words, blankium, right? Blankium. The blankiums will be the stable daughter isotope. We're going to put our blankiums in the plastic bag to keep hold of them, and we're going to put them back in the container because the daughter isotopes stay in the rock. They don't mysteriously go off somewhere. So we want to make sure that they stay a part of the system, which is our container here, just like the stable daughter product would remain in the rock. And that's how a geologist would be able to tell that ratio of parent to daughter product. So we have 28 M&Ms. Everybody has 28, and everybody has their M&Ms. So we're going to close these, and we're going to shake for a few seconds. Here we go. All right, and we're going to open these up and count how many M&Ms have changed or decayed into the stable daughter product, blankium. All right. In go my blankiums to my bag. 2, 4, 6, 8, 10, 12, and 13. All right, so 13 of my M&Ms decayed into blankiums. How about you, Erica? How many?
I got 13 too.
13 as well?
I got 14.
14?
13.
13. All right, so let's record that. So we're going to put our bags of blankiums back into the system, just like the stable daughter products remain in the rock, and we're going to shake again. And then open them up and count how many have changed again into the stable daughter product, blankium. All right, another shake. Put that bag in, and we're going to shake again. Here we go. So now we're on half-life number 3. All right, so another half-life. Here we go. In and close, and we shake. All right, there's 2 blankiums, and as necessary, kind of make it work out. All right, so there's my 2 blankiums, so here we go. Probably another shake or 2, another half-life to go. And how convenient. One of mine changed. Mm-hmm. All right, here we go. Last, another shake. And up, there it is. All of my M&Ms have now decayed into blankium. And there they are. So it took 6 half-lives. All right, so here's the collection of the data from our half-life decay of our M&Ms and blankiums, and you can see that individually we may not have gone down exactly by half, but when you look at the mean or average of the 4 of us, we're pretty much going down by half. We start at 28 M&Ms with no blankiums, and we're going down roughly by half each time. When you look at the mean of the 4 of us, we're going down by 28, it probably goes to about 14 or 15, close to 15, to about 7, to about 3 or 4, to 2, to 1. And then by the 6th half-life, all of the M&Ms have decayed into blankiums. We can see we're all at 28 blankiums and 0 M&Ms. When we graph this out by the collection of the mean, we move to this graph, and we see half-life is plotted along the x-axis with the number of M&Ms and blankiums along the y-axis. And we have this dot to represent the starting value of our M&Ms, which was 28. We had 28 M&Ms in our containers, and that decayed after 1 half-life to about a mean of the 4 of us being about 14 or 15, and that decreased to about 7, to about 3 or 4, to about 2 to 1, and everything by the 6th half-life where we're down to 0. The other line would represent the blankiums, which started out at 0 at the 0th half-life, and then they intersect, the points intersect at the 1st half-life because the numbers should be pretty much the same, 14 and 14, roughly. And then they keep on, the blankiums increase as the M&Ms decrease. But the total number of M&Ms and blankiums should always equal the total number of the original M&Ms, which was 28. And so when we add where the 2 points are at each half-life, it should always be to the total number of original unstable parent isotopes. And when we look at that, that's the half. After 1 half-life, we have half blankiums, half M&Ms. And after 2 half-lives, we have half plus a half of a half, which is a quarter. So 3/4 are now blankiums, with 1/4 being M&Ms. This would be 7/8 because now we're adding half of a quarter, and then that would be 1/8, and so on, 15/16, 1/16, 31/32, 1/32, until after the 6th half-life, we're at 1 total, or 28 original, 28 blankiums and 0 M&Ms. So half each time is changing after a half-life. And that is radioactive decay using M&Ms.
When you have finished watching the video, you'll be taking a short questionnaire that will ask you to rate your confidence on a scale from 0 to 10 in performing all of the learning objectives, where 0 is not confident or sure you can do any of the objectives, 5 is fairly confident or sure you can do some of the objectives, and 10 is very confident or sure you can do all of the objectives.